Hello, everyone. Welcome to this year's EuroVis poster session. On behalf of the poster co-chairs, which are Jan Bischka from Masaryk University in Czech Republic and the University of Bergen in Norway, Johannes Schmidt from EuroVis Center in Austria, and myself, Stefan Meinecke from the University of Southern Denmark. And when I say hello in virtual, it basically means good morning to the Americas, good afternoon to Europe and Africa, and a good evening to Asia and Australia. And so one of the few positive aspects with this virtual form is that we grant access to this very, very important visualization conference to all researchers worldwide who could probably not afford to come to the real conference. So probably we should keep this in mind when organizing future events. One of the more negative things is that a poster session is somewhat that is designed or tailored to take place in a real space, which is also affects the number of submissions we got this year. So from 9 submissions, we accepted 5 posters, which had very good quality. And we want to thank at this point our poster program committee, which you can see here on the right-hand side of this slide. In addition, we also thank our secret best poster committee, which for a reason is not listed here on this slide. Also thanks for that. And I wish to hand over to Johanna, who will give you some more details on the posters, which will be presented in the forthcoming session.
Thank you very much. So those are the 5 posters that got accepted. We have Towards a Collaborative Experimental Environment for Graph Visualization Research in Virtual Reality, a concept describing a collaborative framework for virtual reality systems by Heidrich et al. We have Online Study of Word-Sized Visualizations in Social Media by Huth et al. A study that compares word-size visual summaries of Twitter discussions. We have Unfolding Edges for exploring multivariate edge attributes in graphs by Bludau et al. A poster that focuses on node link diagrams of multivariate graph with an emphasis on edge attributes. We have SimBaTex, which is a similarity-based text exploration application. It's a visual analytics application where users can identify items of interest in text documents. And we have elastic tree layouts for interactive exploration of mentorship by Yan and Ma, a visualization technique to explore mentorship relationships. And to get you a better idea on what the posters are about, we ask the authors to prepare 5 minutes videos to give you an overview, and you now have the possibility to watch those videos.
Hello everyone, I'm Xinyuan Yan. I'm a research assistant at Southern University of Science and Technology. My advisor is Yifang Ma. I'm delighted to present our poster, Elastic Tree Layouts for Interactive Exploration of Mentorship. Mentorship describes mentor-mentee relationship. And previous work mainly visualized mentorship as an academic family tree. But it has some problems. First, node link diagrams lead to space wasting. Second, it only displays a subtree and lacks an overview. Third, it shows too little information. So, accordingly, we propose 3 goals in this project. First, design space efficiency layout. Second, design focus plus context exploration. Third, visualize multiple academic attributes. Our inspiration from elastic objects that can be compressed or be stretched. So, our design is to represent nodes and links as elastic rectangles and bands respectively. In this way, we can achieve multiple operations, such as separation, aggregation, compression, stretch, link stretch, or link compression. Now let me show you a quick preview of this project. The node opacity can be mapped by different attributes such as publication number or citation number. We can select focus and highlight the subtree. We can expand the subtree, show detailed information of the subtree. We use different charts. Besides, we can change the focus smoothly. Now, let's go deeper into how we achieve the three goals. The first goal, we design a space efficiency layout. Mentees of the same mentor are packed together. A gap is set between adjacent families to distinguish each other. We compress leaf nodes to improve the scalability. The second goal, we design focus plus context exploration. To select focus, the node opacity can be mapped by different academic attributes. And then we can select focus and highlight its mentors and mentees. We can further expand the subtree via 3 steps. The first step is to compress or translate nodes to leave space for the subtree so we can expand the subtree and stretch nodes into labels. The second step, we recalculate y coordinates of each layers using fisheye so we can magnify the subtree and compress the context. To make the subtree layout more standard, in the third step, we translate the subtree layout to make it as standard as possible. The third goal, to visualize multiple academic attributes. We deform links for visualizing attributes using different charts. We can change focus smoothly. We select a new focus, we restore the layout and start a new focus. So in summary, in this work we propose a novel elastic tree layout that can achieve a space efficiency global layout and focus plus context exploration, multivariate visualization. In the future, we plan to review more collaborations between mentors and mentees, and visualize mentees who have multiple mentors. Thank you.
Welcome to the demonstration video for SimBaTex, a visual analytics tool which enables the user to assess the similarity patterns of a large set of scientific papers. When the application is loaded, no similarity criteria are specified, so all articles are unclustered and displayed as article icons in the clustering view. This view is used to assess the overall similarity patterns, and on every change of the settings, the articles are clustered together with the article that it is most similar to, if any, under the current settings. The different criterion may be activated, inactivated, or negated, and the current settings show a clustering on articles that are semantically similar and written by different authors. If the similarity is symmetrical, that is, article X is most similar to article Y and Y is most similar to X. This will result in a cluster with only 2 items. and if the similarity is asymmetric, that is, x is most similar to y, but y is most similar to z, the cluster can contain any number of items. Clusters are represented as circles where size encodes the number of articles in each cluster and spatial position and color encodes the average pairwise similarity score within the cluster. The user may also switch between different embedding types to explore which effect this has on the overall clustering. We switch to text similarity only and click a cluster circle. This displays the intra-cluster view, where the pairwise similarity scores are displayed in a heat map matrix and all abstract text are displayed at the bottom of the page. This view allows for analysis of the overall pairwise similarity to determine the level of homogeneity in the cluster. We now activate author similarity and select another cluster. Clicking an article icon in the intra-cluster view displays the target to all view, where an overview of the similarity details of the top 10 best matches for the selected article are displayed as a radial bar chart diagram annotated with a word cloud of matching words. The best match is displayed at the section starting at 12 o'clock and the scores fall off in clockwise order. It is easy to see that for the current settings there are 2 good matches for the selected article. Furthermore, at the bottom of the page, the text pairs are displayed for close reading in a view that uses color to highlight co-occurrences of words to facilitate assessment of the similarity. This view allows for efficient analysis of how similar the selected target article is to any of the other articles in the set. To allow for advanced search, the user may select to track articles on author and/or keyword to see if the selected articles will cluster together. Tracked articles will be highlighted in green-colored frames throughout the views. And in the clustering view, green color will indicate the fraction of tracked articles within the cluster. The darker the green, the higher the fraction. In the current example, we see that some of the articles mentioning the keyword splatting have been clustered together, and by assessing the text, we can determine if they show high semantic similarity or not. This feature is helpful for analyzing questions such as if a specific author tends to write articles on similar subjects, or if articles that mention certain keywords also show high overall similarity. This was a video demonstration of SimBaTex, a prototype visual analytics tool. Thank you for watching.
Hi, I'm David. I'm with the German Aerospace Center, and today I'm presenting you our poster towards a collaborative experimental environment for graph visualization research in virtual reality. When comparing different graph visualization approaches, it's very tempting to just look at the evaluations and say, oh yeah, this one performed better at certain tasks, so it must be the better evaluation approach. However, there are a lot of confounding factors. On the one hand, you have the hardware, like the head-mounted displays, that could vary. And on the other hand, you have the visualization design, like, for example, the shapes or the colors that were used, different metaphors.
Even if they look very similar, they still might differ on the virtual environment or the interaction techniques. So it's not very easy to compare different visualization approaches. For that reason, we are currently creating our collaborative experimental environment, where we want to utilize the same environment for different experiments. And the main idea is that this environment consists of different modules, and we only change one module at a time. And when we measure any differences when comparing those two variations, we can be sure that those differences come from changing this one module. So we can minimize the number of independent variables drastically. A little bit about the implementation. We are using Unity, and we don't want to use too many third-party plugins. So we are using the Unity networking API, we are using SteamVR plugin, and also the SteamVR skeleton input API for finger tracking. And we are using the Neo4j.NET driver to connect to graph databases. Our environment consists of 4 different module types. Those module types are the virtual environment, the graph visualization, the virtual avatar, and the graph manipulation. And we already implemented example modules. So as you can see, the virtual environment consists of a very minimal design with a table at the center where the visualization is displayed on top of it. The graph visualization module consists of a very, very basic graph visualization where the nodes are spheres. The sphere color depends on the node labels, and relationships are just colored lines. Our virtual avatar is a very simple head with floating hands. The fingers can move individually. And the graph manipulation module consists of a natural interaction where you can just grab nodes, and also array pointing interaction where you can point at stuff. And it also consists of a very basic user interface where you can show and hide the node, where you can show or hide the relationships, and where you can highlight the node. This modular approach means that you can add multiple modules. You can also add multiple modules of the same time, and you can also modify those modules. In technical terms, modules are just prefabs that you can load into Unity. And this should help developers and researchers to concentrate on their research in graph visualization. So if someone wants to see if virtual environments make any difference, they can load in all the other modules and only change the virtual environment modules. And this should reduce development overhead, especially with functionalities like collaboration or networking, which normally takes a lot of resources. And like I said, we implemented example modules so everyone can start right away. Or you can use modules of other publications or other evaluations. Future work includes refinement and evaluation of those existing modules. We first have to test if those modules are really feasible for a collaborative, immersive environment. Then we also want to optimize performance. We want to make sure that even very, very large graphs can be displayed in this environment. We want to make the environment open source. And lastly, and that's the main reason why we created this environment, we want to create and evaluate our own graph visualization approaches and be able to compare them in the same environment. Thank you very much for your attention, and maybe we'll see you during the conference. Bye.
Hi, I'm Franziska Huth from University of Stuttgart. I'm presenting our poster, an online study of word-sized visualizations in social media. Word-sized visualizations are small graphics that are usually the size of a word or a paragraph of text. When it comes to showing topic diversity in a social media stream, we wanted to find out how well they can help people understand in which different topic context something is discussed. In a social media thread, people can share posts and comments on a common element. In the Twitter data we collected for this study, that is a controversial video about a car driving into a group of police during protests in the USA. In these comments, different aspects of the common element are discussed in multiple topics, which is not immediately clear to people when they see their social media feed. So how can we make the different topics in the social media stream more apparent? A very simple option would be to add a text label to each tweet that informs people which of multiple topics in the stream it belongs to. Another option would be to use a color coding for each tweet, depending on its topic. The third option we can use is a word-sized visualization, where each colored segment represents a topic cluster, its size is determined by the number of tweets in that cluster, and there is a marker line indicating the topic of the current tweet. We can even show additional information with the mouse-over interaction. We used k-means on the TF-IDF features to cluster the 92 unique tweets we collected as sample data into topic clusters. This is how the different versions look in the Twitter feed. To find out whether people could answer questions about the topics in the Twitter feed faster and with fewer errors with word-sized visualizations compared to other means of conveying similar additional information, we conducted an online study. And because we used the same underlying data and the same questions for all conditions, we did a between-group study, so each participant is randomly assigned one condition. We asked the participants questions about the topics in the social media feed to see how well their study condition helped them understand. We asked about the number of topics, topic cluster size, and topic content, like characteristic keywords and differences to each other. After each question, participants were asked to rate its difficulty, and there was a training phase where participants were shown a Twitter stream with mock data to get familiar with their study condition. First, we were interested in the time it took participants to answer the questions. As for speed, here is in seconds on average with 95% confidence intervals, how long it took participants in each condition to answer the questions and the pairwise difference. We see that there is no evidence that the answering times differ between the conditions. But what about the correctness of the answers? Well, when we plot the error rates for each condition for the different questions, we see that they are also quite similar between conditions. With the text labels, there are more incorrect answers to some questions, but again, we can't see any clear advantage over the word-sized visualizations. One of the questions asked the content of which of the topic clusters is most different to another, which has no correct answer. We see here the answer distribution for each condition, and they are different from word-sized visualizations to the other two. There are two answers that are more common, seen as dark blue cells. In the conditions color and text, there is no such clear distinction, which could indicate that the word-sized visualizations made this task easier. Here are the participants' ratings for the perceived difficulty of the tasks, their confidence in their answers, and their satisfaction with how the topics were displayed in their study condition. Shown are average and 95% confidence interval, 1 is low and 5 is a high rating. And again, we can't see evidence that these ratings are different between the conditions. If you want to see more on the study layout and the statistics, check out the OSF and the poster write-up. As a conclusion, in this study we try to find evidence that with word-sized visualizations people are better at answering questions about topics in a social media stream than with the other two alternatives, but we couldn't prove that. Some things we could look into is modifying the other conditions, add to the other conditions the same amount of information that the word-sized visualizations show, or compare different word-sized visualizations, or measure different parameters. Thank you for listening.
Hi, I'm Martin Bludow, and I'm going to present our research on unfolding edges for exploring multivariate edge attributes in graphs, carried out by Marian Dirk, Christian Tominski, and me. In this research, we are especially interested in the visualization of multivariate edge attributes, which, for example, can include attributes such as edge type, direction, values, uncertainty, or many other things. For these attributes, past research on graph visualization already offers a wide range of potential edge encoding possibilities for node-linked diagrams, such as some more common encoding types that, for example, use color, line thickness, arrows, gradients, or labels, but also more unusual encoding types, for example, small embedded visualizations or varying degrees of oscillation. But typically, these types of edge encodings are applied globally to all edges, which oftentimes leads to visualizations that do not scale well, to cluttered displays, occlusion, or space issues. And even though node-link diagrams are applied widely for various exploration and analysis tasks, approaches using interaction to enhance edge attribute details are so far limited. Mostly interaction with edges is used for selection, to reduce complexity or minimize occlusion, for example by filtering, edge bundling, and by rolling them up. In contrast to these techniques that are intended to reduce overall complexity and to minimize occlusion, our aim is to interactively add more detail to selected edges. With this, we propose unfolding edges as an approach that expands the capabilities for interactive exploration through on-demand detail enhancement of edges and their multivariate attributes. With unfolding edges, we refer to interaction-based dynamic rearrangements in form of situated and transitioned detail enhancements of edges. Here, by enhancing detail only for a selected edge, overall complexity can be kept low, allowing more elaborate edge attribute encoding strategies. And furthermore, by using interactivity and transitions to unfold these additional attribute details on demand and integrating these details into the same view, details can be enhanced without losing the global context, for example, facilitating open-ended exploration of other nodes and edges. Here now you can see two exemplary variations of unfolding edges, one on the top and one on the bottom. In both examples, a selection of an edge triggers a transition towards a new on-demand visualization state. By using semantic zooming and muting down unrelated parts of the graph, the visualization offers more space for adding details while keeping the context intact. In the first example, blending down other edges offers space to separate a selected edge into multiple sub-edges, allowing additional data encoding possibilities for each sub-edge. And in the second example, zoom and rotation are used to bring a selected edge to a horizontal position first, and then the edge is unfolded into a small color-coded timeline representing, for example, historical sources that an edge is based off. We see potential applications of the edge unfolding, especially for fields like historical network analysis, where edges between nodes are usually based on historical documents. Here, observation of individual links between nodes can be of central interest for interpretation and trust in a visualization. Having said that, on the other hand, so far our approach trades the possibility of more elaborate local detail enhancements against global edge encoding possibilities, currently limiting the potential to tasks focused on individual edges. That included, many other questions are still open. For example, how could tasks involving several edges be considered, such as comparison? How could on-demand enhancement of edge details be used for global tasks? Or how to foreshadow enhancement details? First, qualitative interviews and discussions with domain experts already hint to promising results, although formal evaluation is still pending. We are happy to answer questions. Thanks and see you and ciao.
All right. So now when we saw the poster introduction videos, we can proceed with the second part of the poster session. And this will take place in Topia. If you have not yet tried it out, you will find the details about how to log in within the EuroVis welcome email you have received earlier. But please note that the Topia is supported only by the Chromium-based browsers, so such as Chrome, Edge, Opera, or Brave, for example. But unfortunately, Firefox is not among the supported ones. When you log in, you will appear in the circle like this one, and from here you can go to the right and follow the green line until you reach the poster session area. Here you will find several boards like this one, for example, and there should be 6 of those, 5 for each poster you have just seen and 1 extra for the EuroVis 2022. If you click on the board, you can explore the posters in detail, for example, like this one. Or more importantly, once you come closer to the poster avatars standing around the boards, their cameras will pop up and you can actually join the discussion and perhaps ask your questions if some of them pop up into your minds during the videos. So see you in Topia, hopefully soon. And please, if you have any questions, post them on the Discord in poster channel.